Hi, Mick McQuaid here on day 7 of iste 780, Data-Driven Knowledge Discovery. And today is classification day, or I should say today is the first of 2 days dealing with classification. And today is certainly the more difficult of the 2 days. We're going to go through all of the chapter up to the lab, up to and not including the lab. So we're going to talk primarily about 3 different techniques for classification: logistic regression, linear discriminant analysis, and quadratic discriminant analysis. And then we're going to compare those 3 methods along with k-nearest neighbors, which we learned in chapter 2. Let's see, where did we learn that? Section 2.2.3, the classification setting, is where we encountered that. So we're going to compare the 3 of those at the end of the chapter and then do a quick exercise. So I see I'm not at the beginning here, am I? Here we are, classification. Welcome. So classification is a subject we've discussed before, and the introduction to this sort of goes over that same material in some more detail. It mentions that we're going to talk about 3 classifiers. Well, actually, this is a misprint, I think. We're going to talk about logistic regression, linear discriminant analysis, and quadratic discriminant analysis, and then we'll compare them. We already did k-nearest neighbors, as I just said, and then we'll compare them. There are other methods that we'll look at in later chapters. So in addition to the examples that we got in chapter 2, here are some examples of cases where we want to do classification. So let's remind ourselves that classification is the case where y, the dependent variable, or the response variable, or the output variable, is qualitative in nature. And it doesn't matter whether the predictors are qualitative or quantitative. So in this case, we have 3 possible conditions that a patient in the emergency room could have. In this case, we have yes or no as an answer to the question of whether the user's transactions are fraudulent. And here we have the case of whether or not a particular DNA mutation is disease-causing or not. So these are examples of classification problems. And just as in the regression setting, we've got training data, and we would like to build our classifier based on the training data, and then test it, of course, on the test data. And we're going to use the default data set. Now, the default data set in this context means defaulting on credit card debt. So here's a picture of the default data set. And what it is 2 kinds of people: the nice circles and the naughty pluses. So the nice circles are people who did not default on their credit card debt, and the pluses are people who did default on their credit card debt. And we're trying to differentiate them on the basis of 2 variables here. So one of the variables is balance, which we see along this axis, which is in thousands of dollars. In dollars. So a credit card balance of $1,000 apparently doesn't lead to as much defaulting as a balance of $2,000. Along this axis, we try to predict based on income, where we find that an income of $20,000 or $40,000 or $60,000, none of these incomes are more predictive of whether somebody's defaulting or not. We have a mix of pluses and circles in both categories. And here are a couple of box plots that reinforce this idea. And you should be already probably familiar with box plots. I'm going to say they're also called box and whisker plots. And I just want to say a few words about them just in case you glossed over them or forgot them from statistics class. So the box and whiskers plot shows the quartiles and the outliers. So the box always shows the median and the first and third quartiles. And then the whiskers are variable. The whiskers may mean different things. In the case of R, here's the R help screen for box plot statistics, and whiskers are controlled by this setting coefficient, which defaults to 1.5, and it says how far the value of coefficient determines how far the whiskers extend. And so if the coefficient is positive, the whiskers extend to the most extreme data point, which is no more than coef times the length of the box. So in other words, the default is these are 1.5 times the length of the box, no more than 1.5 times the length of the box. And a value of 0 causes the whiskers to extend to the data extremes, and no outliers will be returned. Well, we can tell in this particular case that they did not give a coefficient of 0, because we can see some outliers beyond this whisker. This is a whisker, by the way. The dashed line going to this bar is the whisker. And the length of the whiskers and the length of the box tell us something about the variability of the data. And if we compare two of them, oh, and here's another one with outliers. If we compare two of them, what we want to see is something like this. If I can draw a horizontal line across this, or if it's a sideways box plot, a vertical line, if I can draw a horizontal line like this, then these two are very different. You know, the medians are very different, and the inner quartiles are very different in this case. These two are very similar. I can't draw a horizontal line here that differentiates most of one of the groups from the other group. So this suggests to us that balance is going to be a much better classifier, a much better predictor for classification. The classifier is our machinery of classification. The balance is just a predictor that's got to somehow be used by the classifier machinery. So we see that balance is a far better predictor than income here. Okay, now why shouldn't we use linear regression? I think we did talk about this a little bit in chapter 2, and it's spoken of again here. So imagine that we want to use linear regression, and we have the case of the patient at the emergency room who has one of three possible diagnoses based on the symptoms. They either are having a stroke or a drug overdose or an epileptic seizure. And so we could code Y as 1, 2, or 3 in this case if we were going to do linear regression. And that would be pretty silly because what we're saying effectively is that there's the distance between stroke and drug overdose is the same as the distance between drug overdose and epileptic seizure. And we're also saying somehow that epileptic seizure is more than either of these two, and that drug overdose is less than epileptic seizure and more than stroke. None of these things make any sense at all. In fact, we could reorder them, and of course it still wouldn't make any sense. So instead what we want to do is something like this, which we've already looked at. 0 if stroke, 1 if drug overdose. We can encode something like this using an indicator variable or a dummy variable that we looked at previously. And we could, in the case of there being two classes that we want to classify in, we could say halfway. So if it's 1, it's definitely a drug overdose. If it's 0, it's definitely a stroke. If it's greater than 0.5, we're going to say it's a drug overdose. If it's 0.5 or less, we're going to say it's a stroke. You know, we just divide it right down the middle, this binary case. And in linear regression, we can do this, and we'll get the same, we'll get exactly the same result in linear regression. So what we're effectively doing is checking, excuse me, I don't know why I did that. We're checking the probability. We're modeling the probability of drug overdose. If the probability of drug overdose is less than half, then we're going to say that it's stroke. And of course, the case actually is going to be more complicated if we have more than two classes. But we do have this problem, which is that some of our estimates might be outside the 0-1 interval. And we can see that most easily with a picture. So here's a picture of linear regression contrasted with what we're actually going to use. And in the case of linear regression, the outcome variable we say is 0 or 1. And the linear regression line has some slope, some positive or negative slope. And so that line may cross this axis here. And so it's less, so at a value of balance being less than, I don't know what that number is, maybe 900 or 400 or something like that, some value close to 500. At some value below there, there's a negative probability that person will default. And if we extended this line up, we would eventually find some value where the probability is greater than 1.0 this is the probability of default, so greater than 1.0 probability of default or less than 0 probability of default. So that doesn't make any sense. So if we want to use now there are other models that relax the restrictions of probability, but if we want to use probability, we need a model that has its output trapped between 0 and 1, because all probabilities fall between 0 and 1. There's no such thing as an event that more than happens or less than happens. Either an event doesn't happen, in which case its probability is 0, or it absolutely happens, in which case its probability is 1. There's no way to conceptualize probability outside that unless you get into the realm of something like fuzzy logic, which does take those kinds of things into account as a practical matter. But we don't do that at all here. We entirely use probability here. And so we need some way to trap our output, no matter what our input is, no matter how small nor how large our input is. We want the output to be something between 0 and 1. And it turns out that the logistic function is good for that. Oh, I forgot about my Wikipedia aids. So I wanted to point out, I have a couple of Wikipedia aids back when we were looking at the box plot. I wanted to point out that Wikipedia has a nice list of different uses that the whiskers are put to. So I think this is a good Wikipedia entry, as Wikipedia entries go, the Wikipedia entry on box plot. So you might want to look that up. I also had one on logistic functions. So this just shows the general shape of the logistic function, or a general definition of the logistic function, because it's not completely obvious in the setting that we're using it in the book. They sort of gloss over it, assuming, I think, that you've encountered it before, but just in case you either haven't encountered it before or you've forgotten, this is what the logistic function looks like. Okay, so the logistic function, no matter how big or how small its outputs, returns a value between 0 and 1. So it's ideal for us. So that's the model that we're going to use for that we're going to use for classification, where we have two classes. So the probability of x. This was using a linear regression model, so we're going to use log odds. We're going to use something a little bit different. So here's the logistic function in our context. So the probability of x being modeled as e to some negative x over 1, e to some x over 1 plus e to some negative x. And we can manipulate this model here. This equation is the same thing as saying this equation, and in fact, this will be exercise 4.1 to show that these two expressions are equivalent, and that's not hard to do. We'll talk about that at the end. Okay, and then this is the odds, and what we're going to do is take the logs of both sides, and we have the log odds. The odds are what are used in gambling. I think somewhere here it says something about horse racing. Yeah, here we go. Odds are traditionally used in the case of horse racing. And we're going to take the logs of both sides, and we're going to say that our linear model is the log odds. And that's going to be the output of our logistic regression function. And it's linear. And let's see. Okay, that's just further explanation of that. So when we estimate the coefficients, we come up with this equation. We want to minimize this function. We want to choose values of beta naught and beta 1 that minimize this function. And this is not trivial to do mathematically. So this is one of those things where, because this is not a math course, we're simply going to use R to compute the estimates beta hat naught and beta hat 1 that are chosen, to maximize. I think I said minimize, but this is maximum likelihood. And this is a very common approach, maximum likelihood. So let's think for a second about what maximum likelihood is. We want to find estimates that yield a number close to 1 for all individuals who defaulted, and a number close to 0, as close to 0 as possible for all individuals who did not. That's maximum likelihood. And so we want to find the coefficients that will maximize the likelihood that a defaulter ends up around a 1 and a non-defaulter ends up around 0. And this is a really good and general approach. However, it's not a perfect approach, and later we're going to learn a limitation that it has in this this is what we're going to use, but we have to know about a limitation that it has. And so we might want to relax it a little bit. Okay, so assuming we've allowed R to calculate the coefficients, here they are. So in the case of this, using balance as the predictor, we get the log odds of 0.0055. So what this is and we have a very small p-value. The z statistic is essentially the same thing as the t statistic. It is simply the ratio of the coefficient to its standard error. So if this is large, then we know we've got something, and we're going to have a small p-value. And this, although the fact that this is large and this is small is significant, this coefficient we just ignore. We're only concerned with this coefficient. And what this coefficient is telling us is that for every unit increase in balance, the log odds of default are going to increase by 0.0055. So that means that there is a positive relationship between balance and defaulting. So people with bigger balances are more likely to default than people with littler balances, and the log odds of that happening are this. And if we raise this to the power of e, we would get the odds. And we saw above a formula where we could compute the probability from the odds, and I think the probability is actually computed down here somewhere. And we can just plug this in. So the default probability, so we just plug in our log odds estimate into this expression here, and we get a number below 1% for somebody with a balance of $1,000. So let's take a look at that on our original chart. On our original chart, which is, gosh, it seems like it wasn't that long ago we were looking at this chart. So someone with a balance of $1,000, there's less than a 1% chance. You really can't see it here, but there are, I think, about 9,000 non-defaulters and about 300 defaulters in this picture. So it's a little bit misleading. It looks they look more evenly distributed than that. Whereas for $2,000, default is much more likely. Okay, now I've lost my place. Where are we? Yeah, so a person with a balance of 2,000 stands a 58% chance of defaulting, and that's if we don't know anything else. If all we know about them is their balance, those are the probabilities that we would get from plugging in the log odds there. Okay, and we can also use qualitative predictors. So one of the qualitative predictors in the default data set is whether or not the person is a student or not. So we can create an indicator variable, and if we do this with R will create an indicator variable for us if we've identified student as a yes/no question. And here's the result that we get. There's a very positive, if student is the only thing that we know about, there is a very positive relationship. The z statistic is quite large. The p-value is quite small. So there is a relationship such that for every additional dollar of balance, the log odds increase by 0.4049 that the student will default. So that the person will default if they are a student. There is this increase in log odds. Okay, so we know that this says that students are a bigger credit risk, but it's not that simple. So we get these probabilities where if you're a student, the probability is twice as high as if you're not a student that you'll default. But things are not this simple, and we can very quickly find that out by using multiple logistic regression, which is exactly the same thing, except that we have more predictors. So we have a model that looks exactly the same, except that we have more predictors in the exponents. And what we'll do is check with student and income and balance, all three at once. And we find, of course, that income, as we expect, is not significant. There is no significant difference between anybody based on their income. But we find that student is negatively, has a negative slope and is significant. And so what's happening here is that somehow if we know the balance, then for a given value of balance, a particular student is less likely to default. How can that be? How can it be for a fixed, think about this for a second, for a fixed value of balance? And there's a picture here that I think goes along with the explanation. This whole page I think is an explanation, but I think there's a nice picture here. Students have a tendency in this data set to carry a higher balance. So any given student that you pick is going to be more likely than any non-student because they carry a higher balance, and higher balance suggests a higher likelihood of default. But at any given rate, the curve for the student is below the curve. So these curves, I should point out that this is the overall default rates, and these are the rates for students and non-students. So everywhere, for every value of balance, the value for the default rate for a non-student is above this line. But students have a tendency, as we can see by this box plot, to more of the students are up in this range here, and more of the non-students are down in this range here. So this should warn us of the danger of using simple linear regression in a context where we should be using multiple linear regression. Now, if we have more than 2 response classes, we typically don't use logistic regression. I said linear regression, didn't I? And I meant logistic regression, of course. So we should use we should use multiple logistic regression instead of simple logistic regression because of cases like this. I hope if I make mistakes like this, call me on it if I don't catch them myself. Okay, so logistic regression for more than 2 response classes is typically not done. So this book doesn't go into it, so I'm just going to skip it. And there are some reasons given. These boil down to really one reason, which is the surprisingly unstable thing. These are just variations on that reason. So instead, what we're going to do is linear discriminant analysis. So this is going to be using Bayes' theorem, and it's sort of a not typical way of seeing Bayes' theorem. So here's a picture of Bayes' theorem. This is certainly not the picture that I saw when I first learned Bayes' theorem, and I have another helpful Wikipedia article. So it's very likely, in my mind, that when you first learned Bayes' theorem, you learned it using this notation. This is the common notation for Bayes' theorem, and this is what I would guess that you saw. In fact, this is literally a neon sign expressing Bayes' theorem. It's that common, and so this allows us to separate things out in a way that the textbook seems to like. I don't think I would use pi here. I think that's a mistake because we're going to quickly use pi to mean 2 different things in the same equation, and that's going to be totally confusing. But luckily, we're not going to actually do the math. We're going to show you the math, and then we're going to actually have R do the math for us. So I guess it's okay. So what we need to know is what these symbols mean. So this, you can probably guess, is the posterior probability, and this is going to be recast as P sub k of x. P sub k of x is the posterior probability. Pi of k, or pi of L, is the prior probability for these classes, for the members of these classes. And f sub k of x is some density function that we believe that these classes obey. And so what we're going to do, so what we need to do is find these. If we find these numbers, if we can figure out what these 4, or I guess you could say these 3 numbers are. Is that right? No, these 4 numbers. Yeah, we need these 4 numbers. If you can figure out what these 4 numbers are, then you know what the posterior probability is. And in practice, these are pretty easy to estimate. Pi sub k and pi sub l are easy to estimate because we just compute, as it says right here, the fraction of the training observations that belong to the kth class. So so pi sub k will just be n sub k over n, and pi sub l will just be n sub l over n. So that's easy enough. This is a little bit harder. And so what we're going to do is make an assumption here. And the assumption is going to be kind of a pain, because what we're going to do is make the assumption that this density function is a normal density function. And the normal density function is a little bit ugly. Here it is. This is the normal density function, and it uses the actual pi, the actual 3.14 and so on number as part of that density function. And here's our particular value of x. Here's the mean for the kth class, the variance for the kth class, the standard deviation for the kth class. And this is a function that's somewhat, it can be difficult to work with. So this is a function that we're typically going to have R work with for us. The fact that this is difficult leads to all those tables in the backs of statistics books, because it's difficult to make calculations using this. So, but we're going to just assume all that away because we're going to have R calculating this. So we're just going to plug this in place of f sub k of x here and here. Excuse me, f sub k of x here and f sub l of x here to get the probability. And what we're going to get is a very good approximation to a Bayes classifier. What we're going to get is going to be very simply the two, as a decision boundary, the two means added together and divided by 2, which is going to give us this decision boundary. And estimating that is so good that if we were right, if these two classes do both have a normal distribution, our linear discriminant analysis decision boundary is going to be extremely close. That's the solid line, is going to be extremely close to the best boundary possible, the Bayes decision boundary. So if this assumption holds, so let's just revisit this Bayes theorem here. What we said basically is it's hard to figure this out. If we get lucky, if we guess that these two groups are normally distributed, and we're right, then it's very easy and we're in a very good situation. Okay, what have I missed here? I know I've forgotten something here. Now, and this is cooked data. In the real life situation, we don't know what the Bayes classifier is. This is cooked data just to show us how good it can be if the assumption is correct. I should mention also that LDA is a bad abbreviation for this. In fact, I have the last of my helpful Wikipedia articles. LDA is used in R to refer to latent Dirichlet allocation. I don't know if that's how you pronounce it, but that's how I'm pronouncing it today. This is a very important technique that's also implemented in R. So be careful if you come across the abbreviation LDA. In fact, look, it says right here, not to be confused with linear discriminant analysis. So be careful about that abbreviation. They're using that abbreviation in this book, but any place else you're likely to find that abbreviation being used for latent Dirichlet allocation. And linear discriminant analysis is just going to be called discriminant analysis without the linear on it. We're calling it linear discriminant analysis because we're going to make the distinction with quadratic discriminant analysis in a minute. Okay, and then here are, as I mentioned, these estimates of the mean and the variance are just the same as any other estimates of mean and variance. We take the sum divided by n. We take, for the variance, we do the summation of the deviations from the mean, and we divide it by n, in this case, n minus k degrees of freedom, where k is the total number of classes. And this is a very typical notation for variance and for mean. And here we see the what we said before, the pi hat sub k is just n sub k over n. And this is the actual definition of I almost said the Leighton-Dirichlet classifier, but the linear discriminant classifier is defined. This is what R is actually calculating on our behalf. Let's see, and this is just a description of the picture we just looked at. Okay, so let's move on to the multivariate case. So here's a multivariate picture where we have two predictors, x1 and x2, and these two predictors happen to be uncorrelated. So if we looked straight down on this, we would see a perfect circle here. These two are correlated. They have a Pearson correlation coefficient of 0.7, and so if we were to look straight down on this, we would see an oval pointed toward the upper right-hand corner and the lower left-hand corner. Okay, so these are two very different situations, and that's quite important. What that situation is quite significant in the multivariate case. So here is, again, the oval shape pointing to the upper right-hand and lower left-hand corner. So here's a case of three classes. There's an example with three classes, and this is for cooked data. So this is the population is being taken from three groups. There are three classes here, and this is the Bayes decision boundary between the three classes. And I don't know what this ellipse. Oh, this is a 95% confidence ellipse. So this is like a 95% confidence interval, except in 2 dimensions. And here's the actual sample data, and you can see that the solid line, the LDA decision boundaries, the linear discriminant analysis decision boundaries, are very close to optimal in this case. And it's largely because these three are the same, and we believe that they take on this shape. Imagine if they didn't. See all this relatively tiny area in here where they overlap. If these true shapes were some weird other shapes, the space around these decision boundaries, the space where we're confused, the space where we're not sure, that would potentially grow drastically. And here's the multivariate version of the normal density function. And you know, in the introduction to this book, there was a brief explanation of linear algebra, and I thought it might have been better not to have any linear algebra in there because it's not enough to explain this. For example, this is an inverse matrix. This is an inverse of a covariance matrix. It doesn't tell you anything about inverse matrices. This is the determinant of a matrix. It doesn't tell you anything about that. This is a mean vector. It doesn't say anything about that. But these concepts are actually mathematically pretty simple if you've done a little bit of linear algebra. This right here is simply multiplying a row vector times a square matrix times a column vector. And this is a very typical configuration that you see in linear algebra. But we don't have the mathematical equipment to work with it here. So what you simply need to know is that these covariance, we're going to be dealing with these covariance matrices. We're going to assume that a normal distribution with a mean vector of mu sub k. So this is a mean vector and a covariance matrix. And what R will be calculating is this classifier right here based on this information. So this is the vector matrix version of what we looked at before, what we looked at above the discriminant. This is typically called the discriminant. I don't see that in this book at all, but this is typically called the discriminant. Okay, so, and we see, let's see, some example of this. Here's the next thing I want to talk about. So what the situation that we can get into, and you actually, I think, are going to be asked to calculate this tomorrow in the homework, so it's important that we look at what a confusion matrix is. So we predict something, and something is true. And so we can make a little table like this that we predicted no, and the result was true for 9,000 cases, and yes for 200 cases. We predicted yes, and the correct answer would have been no for 23, and we predicted yes, they will default, and the answer was yes, they will default for 81 cases. So on the face of it, this doesn't look too bad. This looks kind of nice because, you know, we've made these are our mistakes. This is what we've done that's correct, and it looks like we've been correct over 9,000 times. And these are the cases where we were incorrect, which is less than 300 times. So it seems like it's a small fraction. But wait a second. There's something really seriously problematic here. And the problematic thing is that there are consequences to us. So suppose that we're the credit card company, and basically what we use this prediction for is to determine who to deny. You know, your credit card is canceled because we think you're going to default. That's what we're trying to make a decision about. So if we make this decision correctly here, we get all these customers. But if we make this decision wrong here, we have to pay for all these defaulters. If we make this decision correctly for here, we turn away all these people and we don't have to deal with them. So that's nice. And we turn away some good customers that we wish we didn't turn away. But there aren't very many of those compared to the number of good customers that we've got. But this number is really big. You know, it's not really big compared to this number. But it is just really plain big. 252 seems like a lot of people. We would very much like to not have to shell out for the debts of these 252 wastrels. So I had my credit card identity stolen one time, and the person bought almost all professional football memorabilia with it. So I don't know what the heck is the normal case for credit card. You know, and of course, my credit card company took care of it, but you know, somewhere along the line, they had to pay for a bunch of professional football memorabilia. So they don't like to pay for stuff. You know, they would like to basically not have this happen. So so we can say, in a sense, that this is poor performance. We can say that this is, in a sense, poor performance, and we have some words for describing this with very precise terminology. And these words are sensitivity and specificity. So sensitivity is the percentage of true defaulters that are identified, which we only correctly identified 24% of the true defaulters. And the specificity is the percentage of non-defaulters that were correctly identified, which is 99.8%. So that's really nice. We have a really nice specificity, but our sensitivity is very poor. Okay, it's very poor because we're trying to approximate the Bayes classifier. And the goal of the Bayes classifier, if you recall, is to the maximum likelihood function that we spoke about tries to put as many people who do not default, who would not default in the not defaulting category, and as many people who will default in the defaulting category. And so the smallest possible total number of errors is the goal here. Let's take a look at a picture. I'll come back to this. This is really important, and I'll come back to it in a minute, but I want to first take a look at this picture. So here's a picture of our threshold. Our threshold was 0.5. So if they were over 0.5, I think it was, yeah, if they were over 0.5, we classified them as defaulters. So the solid, here, let me just show this. So the overall error rate is this. So if we set a threshold of 0.5, which we did, our error rate is quite low. So here's the error rate over here. This is as low as it gets, or at least on this chart. Maybe it would get even lower if we went over, but this is as low as it gets if we've chosen this, what we did, which is we're putting everybody who's over 1/2 into the 1 bucket and putting everybody who's under 1/2 into the 0 bucket. If we do that, that's what this 0.5 says we're doing. If we do that, we get a very low error rate overall. However, here are the individual error rates for those who default and those who don't default. And notice what happens here is that we have 9,000 people who aren't going to default. So their error rate is very close to the total error rate. The total error rate very, very closely mirrors their error rate. The tiny number of defaulters, there are 300 or 400, some whatever it was, 300 defaulters, have a completely different looking error rate here. So when we choose the lowest total error rate, our error rate for this 300 people, remember this is a rate, this isn't a raw number, our rate for these people is quite high. It's quite high. So if we, instead of choosing the Bayes of trying to estimate the Bayes classifier, if we took our threshold down to say 0.2, we would cut the number of defaulters in half and barely increase the number of good customers that we turn away. And that's exactly what we did in this display right here. We changed to the default probability to, if it exceeds 20%, we're going to turn the customer away. And now what we have done is turned away 235 people, which is still a small fraction of 9,000, but we've almost cut in half the number of people whose credit card bills were stuck with as the credit card company. Now, obviously, this is all from the point of view of the credit card company. If you're a credit card customer, you want them to treat you as well as possible. And in fact, we know that in the credit market in the United States, that's actually what happens. The credit card companies well, not so much credit card, it was real estate in 2008 brought the economy down by giving away too much credit and then demanding that the taxpayers foot the bill for it. So, but we're not, that's a bigger picture social issue. We're just concerned about the mechanics here. And the mechanics tell us that if we choose this classifier that's less than optimal overall, it will be more than optimal for the parts of the situation that lead to bad consequences for whoever we're the agent for. Okay, now here is a Roc curve. So this curve is a popular way of picturing. This is one of several popular ways of picturing how well we're doing. We want to know our true positive rate. We want to know that this line goes up really fast and hugs this corner as much as possible. This is our, oh, I'm sorry, let me put wow, that's a big caption. So we want to know, so this is the no information line. This is what we would do if we had no information. The Roc curve for our model is this, and it's pretty good. A better Roc curve would be one over here, and a worse Roc curve would be one over here. Okay, so the closer it gets to this straight no information line, the worse we're doing. The farther it gets bowed out from that line, the better we're doing. The other things that we are going to use besides the Roc curve, the other indicators of how we're performing are numbers, and they all sort of derive from this table, which tragically is kind of messed up in the textbook. So remember that we had the predictor on the side over here in the previous picture and the true class up here. So they flipped this around. And remember in the picture we had the plus referred to the bad customers and circle referred to the good customers. Now we're on pluses and minuses. But it's basically the same thing. They've sort of changed the terminology around a little bit. And also these are now stars instead of hats. So this is the predicted n that's in the null class, and this is the predicted p that's in the non-null class. So we've got basically these quantities, the false positives, the true negatives, and the false negatives. So here are where we made mistakes, and here's where we did the right thing. This is just the total n and p. This is the total number of observations and the total number of predictors. This is the number of n that we expect to fall into. This is the predicted number of n and predicted number. No, this is not right. Why am I? This isn't. This would be the total. Oh, the total predicted to be non. I see. The p hat is the total predicted to be. So these aren't n and p at all. Forget what I just said. God, I'm so out of it today. This is not p at all. This is these are categories of null, the true null, and the true non-null, and this is the predicted null and the predicted non-null totals. Okay, sorry about that. I don't know where my head is at today. Okay, so but you just have to put up with the absent-minded professor, I guess, and we're going to push on because I don't have time to redo this whole thing. So this is the source of the numbers I'm going to show you now. So here are the numbers. These are used in different fields, in quite a variety of fields. So the false positive rate, false positive over n, the true positive rate, total positive over p, the positive predicted value, total positives over total predicted positives. Oh, p and n, I see not null. It's positive, right? Positive and negative instead of null and not null. I don't know. The terminology is a little confusing here. And these are synonyms used in different fields. So if you've done any work in information retrieval, for example, you know that recall and precision are the main terms that are used. In statistics, generally type 1 error and type 2 error are used. In machine learning, specificity and sensitivity are used. And I don't know where 1 minus false discovery proportion is used. I'm not sure what field that comes from. But in any event, these are key quantities in all kinds of cases for how good a job do we do in predicting classes in all different domains. Okay, and then the last technique that we want to look at, is that right? So we looked at logistic regression and latent and linear discriminant analysis, and now we're looking at quadratic discriminant analysis. And here, basically, the thing that we're going to do is assume, where does it say this? Assumes that each class has its own covariance matrix. That's the big deal here. Each class has its own covariance matrix. And so this is a much more flexible method. And so here's an example of where the flexibility helps and where it doesn't help. So here's a case where the true, let's see what the Bayes decision boundary is, purple dash. So the true is here. So this is, again, a cooked data set with the true values known. So the true values here, and here the true decision boundary is more complicated. And quadratic discriminant analysis is more flexible. It can change and adjust to this more complex curve than can linear discriminant analysis, which is stuck with these straight lines. So it does a much better job. But see, the problem is it does a much better job if the underlying phenomena has this shape. And we never know for sure. We're always sort of, trying to use domain knowledge to guess what the appropriate shape is. So we always have to have a mix of knowledge of this kind of stuff plus domain knowledge kind of stuff. And that's why this stuff is so hard, because the people with the domain knowledge don't understand quadratic discriminant analysis, and the people who understand quadratic discriminant analysis don't necessarily understand, say, the credit card market. So people have to work together in partnership with this kind of information. Okay, so here's a comparison of all these methods, and there are basically, the comparison boils down to some pretty simple things here. So first of all, what's the difference between linear discriminant analysis and logistic regression? So linear discriminant analysis makes this assumption of the common covariance matrix with a Gaussian distribution. And so it can do a terrific job in that case. If those assumptions, the Gaussian distribution and the common covariance matrix, are not met by a real-life situation, then logistic regression will perform better. The other two methods, k-nearest neighbor and quadratic, are both much more complicated. Both can fit much more complicated models. So, and k-nearest neighbors is completely non-parametric. So if the boundary is highly nonlinear, if the decision boundary is really weird, then we can expect k-nearest neighbor to dominate. But k-nearest neighbor is completely non-parametric, so it doesn't tell us anything about the predictors. It's very much black magic. Quadratic is a little bit of a compromise between, a little bit of a bridge between the two linear approaches and the totally non-parametric approach. So it assumes a quadratic decision boundary, so it is more flexible than the linear methods. But it's not as flexible as KNN. But it does perform better than KNN if you have a limited number of training observations, because it makes some assumptions about the form of the decision boundary. So if you have a limited number of training observations, you should probably make some assumptions. Okay, so now there are 6 different scenarios here, and there are box plots here. There's a lengthy description. I'm not going to go into the lengthy description, but there are some, whoops, what did I skip? Oh, here they are. So here are the 6 cooked up scenarios to show how some of these dominate in some situations and some dominate in other situations. And I think you should go back and forth between these and the individual scenario descriptions to see which dominates where. I think that'll give you a good intuition for it. And then look at this summary. So in this this paragraph sort of summarizes the most important results here. I think other than that little table that showed the sensitivity and specificity along with the synonyms from other fields, the thing that I would most like you to take away from this chapter is this part right here. No one method will dominate. If the decision boundaries are linear, LDA and logistic regression will perform well, LDA performing better if assumptions about Gaussian distribution and common covariance matrices are met. If the boundaries are not moderately nonlinear, quadratic may be better. And for much more complicated decision boundaries, a non-parametric approach may be better. But if you use a non-parametric approach, you have to be very careful about the level of smoothness that you choose, and that becomes an issue in some of the ones where the errors are worse, like this one is predicated on a bad choice, I think. Okay, so that's about it for this chapter. Tomorrow we'll go over the lab. The only other thing I wanted to talk about briefly here is exercise 4.7.1. I think this is, even though this is a conceptual exercise and the ones I want you to turn in are mostly the applied ones, this might be useful to go over. So using some algebra, prove that expression 4.2, which is an equation, is equivalent to expression 4.3, which is another equation. In other words, the logistic function representation and the logit representation are the same, mean the same thing. And so I'd like you to go over that, and I will, by the time that you do that, I will have put a picture of me doing it by hand on my courses that you can look over. You can also probably find a solution to it online. But what I want you to keep in mind when you're doing this is the simplest way to do it. Now, it may just be obvious to you if you've had enough of a math background. This may just be a trivial exercise for you, but if the solution is not obvious just when you glance at the two expressions, do this. Try forward chaining from one and backward. Think of one as the starting point and the other one as the finishing point, and try forward chaining from one and backward chaining from the other, and you'll find that in only about, I don't know, let me just take a look at where I did this. 3 or 4 steps each way, about 3 steps each way, you'll see the equivalent expressions. So so do that today, and we'll do the lab tomorrow. Thanks very much for your attention. Take good care.